Why passenger jets still fly at the same speed. Look out the window during a long flight, and almost nothing suggests that you are moving at extraordinary speed. The cabin is calm. A glass of water barely trembles. Far below, the ground seems almost motionless. But outside that window, the airplane may be crossing the sky at roughly 560 miles per hour, more than 7 times the speed of a car on the interstate. And here is the strange part. Airliners were already flying at nearly this speed more than half a century ago. Since then, engines have become more powerful. Wings are designed by supercomputers. Modern aircraft are built from advanced alloys and carbon fiber composites. We have sent machines beyond the solar system. Yet a passenger jet built today usually cruises at about Mach 0.78 to Mach 0.85, almost exactly where commercial aviation settled decades ago. Why? Why did aviation improve almost everything except speed? Why does pushing an airliner only a little faster become so difficult, so expensive, and sometimes so dangerous? And could a new generation of quiet supersonic aircraft finally change the equation? The answer begins with an invisible transformation in the air itself. At about 35,000 feet, a modern wide-body jet may cruise near Mach 0.85. Depending on temperature, that is roughly 560 to 570 miles per hour through the surrounding air. The number shown on a passenger's flight map may be higher or lower because that display usually shows ground speed, which includes the effect of the wind. For engineers, the more important number is Mach. Mach number compares the airplane's speed with the local speed of sound. And the speed of sound is not fixed. It changes with temperature. In the cold air near cruising altitude, sound travels more slowly than it does near the ground. That means an airliner does not have to reach the familiar sea level figure of roughly 760 miles per hour before parts of its airflow become supersonic. The airplane itself may still be below Mach 1, but air accelerating over the curved upper surface of the wing can move faster than the airplane. At normal cruise, small regions of that flow may already reach supersonic speed. A short distance later, the flow has to slow down again. It cannot always do that smoothly. A shock wave forms on the wing, a thin, abrupt jump in pressure, density, and temperature. Behind that shock, the airflow may separate from the surface. Drag rises. Lift can change. Buffeting may begin. Control surfaces can become less effective. This is the transonic regime, the complicated territory around the speed of sound. It is not a solid wall, and an airplane does not slam into it like concrete. But it does create an aerodynamic price that becomes steeper very quickly. Engineers call one important threshold drag divergence, Mach number. Beyond it, a small increase in speed can produce a disproportionate increase in drag. To go only a little faster, the engines must deliver substantially more thrust and burn more fuel. This is the first reason passenger jets gather around the same cruise speed. They are designed to fly just below the point where the aerodynamic bill begins climbing sharply. Modern wings delay that bill with 2 major ideas. First, they sweep backward. A swept wing reduces the component of airflow that strikes its leading edge directly, postponing the strongest compressibility effects. Second, most modern airliners use supercritical airfoils. Their carefully flattened upper surfaces weaken the shock wave and help the aircraft cruise efficiently near Mach 0.8 or Mach 0.85. These designs did not make speed irrelevant. They allowed airlines to spend the improvement on efficiency instead. NASA's supercritical wing research showed that manufacturers could either move closer to the sound barrier or remain at familiar speeds and save fuel. The market overwhelmingly chose fuel savings. That decision reveals something essential about an airliner. It is not designed for one spectacular moment at cruise. it has to perform an entire mission. The same wing that slices efficiently through thin air at 35,000 feet must also lift a fully loaded aircraft from a runway at less than 200 miles per hour. It must remain controllable during turbulence, approach, landing, and an engine failure. It must carry fuel, landing gear, control systems, and sometimes hundreds of passengers. A very thin, sharply swept wing is excellent for high speed, but it provides less room for fuel, creates structural challenges, and performs poorly at low speed unless engineers add more weight and complexity. A large, straighter wing is excellent for takeoff and landing, but it produces too much drag near the sound barrier. Every airliner is therefore a negotiated settlement between incompatible demands. Speed is only one vote. The hidden cost of that settlement became visible during the first years of the jet age. On January 10, 1954, BOAC Flight 781 departed Rome for London. The aircraft was a de Havilland Comet, the world's first commercial jetliner. It flew higher, faster, and more quietly than the piston-powered aircraft it was replacing. About 20 minutes after takeoff, the Comet broke apart over the Mediterranean. All 35 people aboard were killed. Investigators faced a mystery. There was no intact aircraft to examine, so wreckage was recovered and the fuselage was reconstructed. Another Comet airframe was placed inside a huge water tank. By repeatedly pressurizing and depressurizing it, investigators recreated the stress of flight after flight. The result changed aircraft design. The Comet's pressurized cabin expanded slightly at altitude and contracted again after landing. Repeating that cycle thousands of times produced metal fatigue. Stress became concentrated around openings and sharp corners, including window and antenna cutouts. Tiny cracks grew until the structure failed explosively. The lesson was not that 35,000 feet, or 560 miles per hour, created a universal speed limit. The lesson was that high-altitude jet travel places repeated loads on a structure that can appear perfectly healthy until it suddenly is not. Later airliners used stronger construction, improved inspection methods, and openings with more rounded corners that distribute stress more smoothly. The calm cabin of a modern jet exists because engineers learn to control pressure cycles that passengers never feel. But the higher an airplane climbs, the more another invisible margin begins to shrink. Thin air reduces drag, which is good for efficiency. It also reduces the lift available at any given true airspeed. To remain airborne, the airplane must move fast enough through that thin air. Fly too slowly, and the wing can stall. At the same time, the aircraft must remain below its high-speed Mach limit, where shockwaves, buffet, or structural loads become unacceptable. At very high altitude, the low-speed boundary and the high-speed boundary can move closer together. Pilots historically called the extreme version of this narrowing coffin corner. Modern transport aircraft use carefully calculated flight envelopes, automatic warnings, and control laws to keep operations safely away from those boundaries. One famous accident is often described incorrectly in this context. On June 1, 2009, Air France Flight 447 was cruising over the Atlantic at 35,000 feet when ice crystals temporarily obstructed its pitot probes. The flight computers lost reliable airspeed information, the autopilot disconnected, and control logic changed. In the confusion, the pilots made sustained nose-up inputs. The aircraft climbed, lost speed, entered an aerodynamic stall, and remained stalled until it struck the ocean. All 228 people aboard were killed. Flight 447 did not crash because it simply flew too close to the speed of sound, and it was not a textbook case of an airplane being trapped between stall and overspeed. The official investigation described a chain involving unreliable airspeed, automation changes, control inputs, warning interpretation, training, and the crew's failure to recognize the sustained stall. Its real lesson is more important than the myth. At cruise altitude, speed information and energy management matter enormously. Automation can protect an aircraft only while its sensors, logic, and human operators understand the same situation. Physics never leaves the cockpit. Even when every safety margin is respected, flying faster creates a brutal economic problem. At subsonic speed, aerodynamic drag already grows rapidly as velocity increases. Near the transonic boundary, wave drag joins the equation. More thrust requires larger engines or higher engine output. More output requires more fuel. More fuel adds weight. More weight demands more lift, which creates still more drag. This feedback loop can turn a modest improvement in travel time into a major increase in operating cost. In 2001, Boeing revealed the Sonic Cruiser, a radical airliner concept designed to fly as fast as Mach 0.98. It promised to cut long-distance flight times by roughly 15 to 20% without crossing into sustained supersonic flight. On paper, it looked like the next step after the conventional jet. But airlines were being asked to choose between two different kinds of progress: arrive somewhat sooner or use dramatically less fuel. They chose efficiency. Boeing ended the Sonic Cruiser program and redirected key technologies toward what became the 787 Dreamliner. The 787 cruises closer to Mach 0.85, but its composites, engines, and aerodynamics reduce fuel consumption compared with the aircraft it replaced. The reason is visible in any real trip. A 15% improvement in cruise speed does not make the entire journey 15% shorter. Passengers still travel to the airport, pass through security, wait at the gate, taxi, climb, descend, collect baggage, and reach their final destination. A faster airplane can save meaningful time on a long ocean crossing, but it cannot accelerate the rest of the system. For most travelers and airlines, a lower fare is worth more than an hour saved. In fact, airlines make this trade on nearly every flight through a value called cost index. The flight management computer can be told how heavily the airline values time compared with fuel. A low cost index favors slower, more economical flight. A higher cost index tells the aircraft to accept greater fuel burn in exchange for arriving sooner. If a flight is running late, the crew may be able to increase cruise speed within the approved envelope, but the result is rarely dramatic. Near the airplane's normal operating point, burning noticeably more fuel may recover only a few minutes. A strong tailwind can change the arrival time far more than pushing the throttles forward. This is why a flight tracker can create the illusion that one airliner is much faster than another. An eastbound jet crossing the Atlantic may show a ground speed well above 650 miles per hour, while remaining at an ordinary Mach number. The airplane is not breaking its aerodynamic limits. It is riding inside a river of fast-moving air. The opposite happens against a powerful headwind. Ground speed falls even though the wings experience the same safe airflow. For the aircraft, the atmosphere is the reference. For the passenger watching the map, the Earth is the reference. Mixing those two speeds makes the supposed 590 mile per hour limit look much more precise than it really is. There is no single speed selected by law or hardware. There is a small operating neighborhood where the aircraft performs best, and the exact point moves with altitude, temperature, weight, wind, schedule, and fuel price. There was, however, an aircraft that refused this compromise. Concorde entered service in 1976 and cruised at about Mach 2, roughly 1,350 miles per hour, at altitudes near 60,000 feet. It could cross the Atlantic in less than half the time required by a conventional airliner. Concorde proved that supersonic passenger travel was possible. It also demonstrated why possibility and practicality are not the same thing. At twice the speed of sound, compressing and disturbing the air heated the aircraft's skin. Near the nose, temperatures could approach 260 degrees Fahrenheit. Concorde was designed to tolerate the effect, but its aluminium structure still expanded by roughly 7 inches during supersonic cruise and contracted again after landing. That was not the metal melting. It was controlled thermal expansion, anticipated by engineers and accommodated with special joints, materials, paint, insulation, and maintenance procedures. The larger problem was everything required to make that performance routine. Concorde carried about 100 passengers. It consumed enormous amounts of fuel. Its engines were optimized for a flight regime completely different from that of a conventional airliner. Its maintenance was specialized, its ticket prices were high, and the shape that made it efficient at Mach 2 made it less efficient at ordinary subsonic speeds. Then there was the boom. A sonic boom is not merely the instant an aircraft breaks the sound barrier. A supersonic airplane continuously generates a system of shock waves. As it travels, those waves sweep across the ground in a long corridor beneath the flight path. To someone below, the pressure change can sound like a sudden double explosion. Traditional supersonic aircraft can rattle windows and startle entire communities. The faster flight may be happening miles overhead, but the cost is paid by everyone underneath it. In 1973, the United States adopted rules that generally prohibited civil flight above Mach 1 over land unless specially authorized. That restriction made the business case for a supersonic airliner much harder. A plane designed for Mach 2 could use its defining advantage mainly over oceans. On many routes, it would have to slow down and behave like a far less efficient conventional jet. This is why modern airlines did not simply build another Concorde after it retired. To succeed, a new supersonic aircraft must solve several problems at once. It has to reduce the boom that reaches the ground. It must meet modern airport noise standards during takeoff and landing. It must use much less fuel. Its engines must work efficiently at both subsonic and supersonic speeds. Its structure must survive heat and pressure cycles for decades. And the ticket must be affordable enough to fill the seats. Solving only the speed problem is not enough. That brings us to the most important question. If conventional airliners have remained near Mach 0.85 for decades, does that mean aviation stopped advancing? No. The speed displayed to passengers stayed similar while almost every other measure improved. Jet engines became dramatically more efficient and quieter. Navigation became more precise. Composite structures reduced weight. Weather forecasting improved. Long-range twin-engine aircraft replaced many 3- and 4-engine jets. Reliability increased so much that 2-engine airliners routinely cross oceans and polar regions. The industry did not fail to make aircraft faster. It deliberately invested in carrying more people, farther, more safely, with less fuel and less noise. Mach 0.85 is not a hard law of nature. It is the center of an enormous optimization problem. And now that optimization may be changing. On June 6, 2025, a United States executive order directed the Federal Aviation Administration to move away from the blanket prohibition on civil supersonic flight over land and towards standards based on the noise that actually reaches the ground. That distinction matters. It does not mean that every supersonic aircraft can suddenly race over American cities. As of 2026, the regulatory system is still being rewritten, and civil supersonic operations over land remain subject to federal restrictions and authorization. The goal is to replace a simple speed limit with a measurable noise limit. At the same time, NASA is testing the technology that could make such a rule possible. The X-59 is an experimental aircraft built for NASA's Quest mission. Its long, needle-like nose and carefully shaped body are designed to prevent shock waves from merging into the powerful pattern produced by a conventional supersonic aircraft. Instead of a window-rattling boom, the objective is a much quieter thump. The X-59 is not a passenger airliner prototype. It is a research aircraft built to collect the evidence regulators need. In October 2025, it made its first flight. Then, on June 5, 2026, the X-59 exceeded the speed of sound for the first time, reaching about Mach 1.08, roughly 713 miles per hour at 43,400 feet. That flight did not instantly begin a new age of supersonic travel, but it crossed an important threshold. For the first time in decades, American technology and regulation are moving together toward the same question. Not whether an aircraft is supersonic, but whether people on the ground can live with the sound it creates. Future high-speed airliners may therefore compete in two races at once. One race will be measured in miles per hour. The other will be measured in decibels, fuel burnt, maintenance hours, and dollars per seat. The winner will not necessarily be the fastest aircraft engineers can build. It will be the fastest aircraft that airlines can operate, passengers can afford, regulators can approve, and communities below may barely hear. That is why your next flight will probably still cruise near 560 miles per hour. The airplane is not struggling against an arbitrary limit. It is balancing on a narrow point where aerodynamics, safety, cost, noise, and human convenience all agree. For more than 50 years, that balance favored efficiency over speed. Now, for the first time in a generation, the balance may be moving again. If you enjoy documentaries that uncover the hidden engineering and physical laws shaping everyday life, subscribe to Frontiers of Reality. The world is full of ordinary machines performing extraordinary negotiations with nature. And sometimes, the most revealing question is not how fast they can go, but why they choose not to.